here we're going to start solving differential equations, and the kind of differential equation we're going to solve is called an initial value problem, abbreviated IVP here. And what that is an ordinary differential equation plus an initial condition. An initial condition tells you kind of how things start out. So if we're thinking about the independent variable being time, an initial condition is what's the value of the dependent variable when time equals 0. And we're going to solve the easiest kind of initial value problem, which is a differential equation of this form. Okay? And the key thing to note here is that the right-hand side is a function only of the independent variable. So here f of t is like a placeholder for some expression involving t. And think about what this says. It says there's an unknown function y, its derivative is some formula in terms of t. How do you find that? How do you solve it? Well, you did this a million times when you took calculus. You just have to anti-differentiate, right? And then, of course, we have our initial condition over here. So in short, when you see a differential equation of this form, it's one that you can solve directly by anti-differentiation. So let's go ahead and do a couple examples. First, we can take a look at dx dt equals t cosine t, where x of 0 equals 3. And this is one that we can solve by integration by parts. So when I look at the right-hand side, I see a product of things. I'm going to think of t as being u, and cosine t as being dv. And with those choices, we have that du is 1 dt, and v is going to be equal to sine t. So the integration by parts formula says that the integral of u dv is uv minus integral of v du. Substituting, that gives us x equals t sine t minus integral of sine t dt. This remaining integral is really easy. We can just do that directly. So we get t sine t plus cosine t plus a constant. To find the value of the constant, we have to substitute the initial condition up here. So I substitute that when t equals 0, x is equal to 3. And then I equate that to what I get when I actually plug 0 into the formula, like 0 sine 0 plus cosine of 0 plus z plus c. That gives me 0 plus 1 plus c right here. So 3 equals 0 plus 1 plus c, so c equals 2. So the final answer is x of t is t sine t plus cosine t plus 2. Here's another example. We have dy dx is equal to 3x plus 7 over x squared plus 5x plus 6, with y of 0 equals natural log of 18. And we got to find a way to anti-differentiate this expression here, and the way we're going to do that is by using this technique called partial fractions. And partial fractions is possibly appropriate when we see a rational expression of a variable, right, like a quotient of polynomials, where the denominator is factorable. So here the thing I notice is that x squared plus 5x plus 6 can be factored as x plus 2, x plus 3. And we guess some coefficients on top, and so I guess a over x plus 2, and b over x plus 3. And what I'm sort of doing here is I'm taking this expression, and I'm wanting to write it in a different way. You'll see why momentarily. And I'm trying to find what numbers a and b will make these two things equal each other. So the next step is that you take the expression on the right-hand side, and you combine it back into a single fraction. So you have to like cross-multiply and write over a common denominator, and I get ax plus 3a plus bx plus 2b over x squared plus 5x plus 6. And so, since the left side has to equal the right side, and the denominators are the same, it means the numerators are the same. So 3x plus 7 has to equal ax plus 3a plus bx plus 2b. And when you have two polynomials equaling each other, it means the coefficients have to equal each other at each degree. So what that means for us is that at the power of x to the 0, that's the constants, we have 7 equals 3a plus 2b. And at the power of x to the first, we have 3 equals a plus b. That's a system of two equations and two unknowns. You can solve it to find a equals 1 and b equals 2. So all of that work was just, so far, to write the original differential equation in a different way. We found that we could write it as dy dx equals 1 over x plus 2 plus 2 over x plus 3. All right, So now what? Well, now we have to anti-differentiate. And the whole reason we did this is that written in this form, the right-hand side's easy to anti-differentiate. It's just some natural logs. So y of x is natural log of x plus 2 times the natural log of x plus 3 plus a constant. Now I'm going to use the fact of the initial condition. So when I plug in 0 for x, I get natural log of 18. That's what the initial condition prescribes. And then when I plug into my expression, I get natural log of 0 plus 2 natural log of 0 plus 3 plus a constant. Well, it turns out that these two terms together equal natural log of 18, so that's going to cancel with the left-hand side, and we're left with the constant c equals 0. So the final answer is here. Y of x is natural log of x plus 2 natural log x plus 3. All right, final example. We can even start with the second derivative and use this procedure twice if the right-hand side is only a function of the independent variable. So we start with second derivative of x equaling 2, and 2 is a constant, but a constant is a kind of a function of the independent variable. So we can still anti-differentiate. I anti-differentiate once, I get dx dt is 2t plus a constant. That's the independent variable t. And then we go on and we can anti-differentiate one more time, and we get x equals t squared plus c1t plus c2. If we would like to know what the unknown constants are, we need some initial conditions. Since our differential equation involved a second derivative, we need two initial conditions to figure out the two unknown constants. I'm going to take x of 0 equals 1 and x prime of 0 equals 2. So I plug x of 0 equals 1 into here, the expression for x, and I find that 1 equals c2. And then I plug x prime of 0 equals 2 into the equation for the derivative of x, and I find 2 equals 2 times 0 plus c1, so we find c1 equals 2. Putting it all together, we have x of t equals t squared plus 2t plus 1. That's it, and thanks very much for listening.